viewers. Welcome to my YouTube channel. You are watching Ali Maths Online, and as you know, we have started a series lecture on the fractional calculus. In the last lecture, I have drawn a relationship for the Grunwald-Letnikove Fractional Derivative. In this lecture, we will extend this expression to find some useful results. As we know, the limits involved in the expression is quite complicated to draw the results for the fractional order derivative. So we will try to draw another formula which is useful for us to draw the results in the fractional calculus. Okay, let me start with the Grunwald fractional derivative. The formula of the Grunwald fractional derivative is limit tends to infinity 1 over a raised to power alpha summation I 0 to n minus 1 raised to power I, a combination of alpha and I f of t minus I of h, where h is t minus a over n. Okay, by the definition of the combination of alpha of I, we can write in the form of the factorial, alpha of factorial over I factorial into alpha minus I factorial. So if we extend the formula of the alpha factorial, then the result will be alpha and alpha minus 1 and so on, alpha minus alpha I minus 1 and alpha of minus I factorial over alpha factorial I factorial and alpha minus I factorial. So we have the same results, so we can cancel out this. After cancelling, we will replace alpha by minus alpha. It is only about if we reduce the order of the fractional calculus, if we reduce the order of a derivative, then it will turn into the integration. So if we replace alpha in this relationship to minus alpha, so our combination will be turned into, or this relation will be turned into the integral form. So we can write it as that the result of minus alpha of I combination can be written as, if alpha is replaced by minus alpha, so the result will be minus alpha minus 1 and so on, alpha minus I minus 1 over I factorial. Okay, here we can see that we have a number of terms in this relation is alpha minus alpha minus 1 and so on, minus alpha into minus I minus 1. So we can say that the number of terms from minus alpha to minus 1 are I minus 1, and the one term is minus alpha. So the whole number of terms are I, and we are taking minus common from this expression, so the power will be I. Okay, then what will be next? If I take minus common, the result will be there will be plus 1. There will be plus 1, and take minus common, then there will be a plus here, and it's a minus over I factorial. If I switch the order of the this expression, so we can write it as alpha plus 1 minus alpha plus I minus 1 and so on in the previous order. So it's alpha and alpha plus 1. Okay, here we can write it as alpha plus 1 into alpha. Okay, if I divide and multiply by alpha minus 1 factorial, so alpha minus 1 factorial here and alpha minus 1 factorial here, so the whole expression will be alpha plus I minus 1 factorial over I factorial into alpha minus I factorial. So by using the definition of the gamma function as we described in the previous lecture, so gamma of n will be equal to n minus 1 factorial. So we can write this function as alpha plus I, so the minus 1, so it can be written as the gamma of the alpha plus I, and here's the factorial function is alpha minus 1, so we can write this as gamma of alpha. So the minus alpha of I combination will be equal to minus 1 raised to power I gamma of alpha plus I factorial and gamma of alpha. As we didn't turn this I into the summation into the gamma form, because we explained before in the lecture that I is the basically indicate the series term as mentioned here. Okay, as I mentioned here is that I is equal to 0, so it is the parameter which can be used to expand the series. So this will be integers, a positive integer. So with no need to transform this value into the gamma function. Okay, if we put this value of minus I of something into this function in the form of Grunwald-Letnikove Fractional Derivative, so the alpha is replaced by minus alpha and the whole expression is same as it, but the value of the combination of alpha and I, as we replace alpha by minus alpha here, the result will be that, so the result will be put here, the summation will be turned into a minus I. That's the value of this expression. Okay. Okay, if we plug this value into this function, the result will be minus 1 raised to power I gamma of alpha plus I, as mentioned here, over gamma of alpha. So this is minus 1 raised to power I and minus 1 raised to power I. So after simplifying this will be minus 1 raised to power 2I. If the power of the minus number is an even number, so the result will be turned into a positive number. So minus 1 will be equal to 1. Okay. The expression will be equal to the minus of alpha. Sorry, here is the 1 over h. 1 over h. Okay. So as the power is minus alpha, so it can be turned into h raised to power alpha. And summation same as it. This value is equal to 1, and the gamma of alpha plus I over gamma alpha, or I factorial into t minus ih. Okay. That's can be written in the form of integral. That's I indicates the integral of alpha order f of t. The f of t is the function which needs to be integrated. Okay, if we substitute alpha is equal to 1, which is the ordinary order of the integral, that's maybe we need we will study in the classical calculus. Okay, if we put alpha is equal to 1 here, the value will be limit n approaches to infinity, same as it, h is power alpha. So h in the summation is I from n from I to n, and the gamma will be equal to I plus 1, as alpha is 1 and gamma of 1 is I, so t minus I of h. Again, by using this definition of gamma, we can write this as the gamma of I plus 1 will be to I factorial. So this gamma function of m1 is equal to I factorial will be cancelled out. So the gamma of 1 is also 1. So the function will be turned into f of t minus h, which is the most famous definition of the Riemann Liouville Fractional Integral for order 1. Okay, to draw the formula for the generalized form of the integral with the Riemann Liouville integral, we will generalize the integral form of the classical calculus. Okay, let me have a function y is equal to f of t, which is integratable in the interval of a to b. So we can write this as f of t dt, which interval is a to b. To find the precise sets of this function, we will turn the limit into the nth equal rectangles. So equal rectangles. So if we take the height, so the width of the each rectangle is h. So h will be b minus a over n, where n is the number of the partitions that we made for the interval ab. So if we plot the graph of the function, so we can say that if we take h as the width of the triangle, as we say like that, a triangle is equal, so the width of e triangle will be equal. Okay, so if we take initial point of the interval of the integral is a, so t is equal to a, then the value of the function will be at that point is f of t. Value of that point is f of t. If we extend the values at t plus h, so the function values will be f of t plus h, same as t plus 2h, and so on for t plus n of h, where the value of b, so the function value will be equal to that. If we write, I calculate the result of this curve, so we can say that this will be the area under the curve. So we find the area of the curve the area under the curve. We will find the integral, which is from a to b f of t d of t. Okay, so that will be the sum of the areas of all rectangles we mentioned here. So we can write is that the area of the rectangle will be length multiplied by width. So that's the length is f of t and the width is h. So width of for each rectangle is same. So we can write this h of f of t plus h of f of t plus h, and up to so on h into f of t plus n of h. So we can write this function by taking h common. So we take h common from this expression. So the integral will be equal to h into f of t and so on. So we can write the form as a Smithson form, which mentions here. Okay, if we see this form is quite same as we mentioned in this in equation A. So as we see that there is a relation which is h summation from I to n, and f of t plus I of h is quite same as mentioned here, which is the Riemann fractional integral. So we can say that if the expression, this expression is an integral, so here's this Riemann integral, this expression of the integral is also can be written as the form of the integral. So we will extend our results towards the Riemann integral. Okay, here's the main difficulty in this expression and this expression is that here's the value depends upon t plus I of h, but here's the value is t minus I of h. So if you want to get the f of t, so we'll substitute t as x minus I of h. If I replace this t by t of I of h, then the result will be turned into f of t. So we will understand from here that we need to substitute some kind of this substitution in this expression to get the integral form. Okay, to get the integral form. Okay, here we can see that here's the small partitions, which is here. So these are the basically errors because this is a form of a triangle, and this is also form of triangle, also form of a triangle, and also form of triangle, and this is also form of triangle. So if we want to reduce our error, we will apply a limit n approaches to infinity on this expression, so the error will be reduced as we make more partition for this function. So each partition will behave like a rectangle. Okay, so this expression and this expression is quite same as per limit. Okay, so I had discussed before that if we replace t by t minus I of h, then the z will be turns to this. If I replace t is equal to t minus I of h, so the z will be turns into this integral. So we need to make some substitution in this z to get this form of the integral. Okay, let me have this function. We substitute h is t minus a minus 0 over n. So here's t minus a is the value of b as mentioned here, the upper limit of the integral, and the 0 is the value of the a, which is the lower limit of the integral. So the result will be equal to 0 to t minus h, as t is mentioned in the limit, so we can use it as a variable of the function. So we will use the variable as x. Okay, so f of t minus x is a d of x. Okay, so if we substitute t minus h as t minus x, as limit x approaches to 0, u approaches to t, and if x approaches to t minus h, then the u will be approaches to a. If we take derivative of this function, this is d of u, t behaves like a constant because that's in limits, so x behaves like a variable, so du is equal to minus d of x, so the value will be equal to this function. Okay, here we seen that is the negative sign. Okay, to remove this negative sign, we will switch the integral, so the limits of the integral will be changed to reduce this negative sign. Okay, by shifting the limits of the integral, we will get f1 of f of t, that is here, which converts into the integral as we mentioned and generalized from the classical calculus. So this is a to t f of u into d of u. Okay, now we will move towards the results to approximate alpha order of the integral, which is arbitrary order of the integral. So we will put alpha is equal to 2 and 3 and so on n, and then we will replace n by the an arbitrary number that will be alpha, which may be real, complex, or as we have the integral form of the Riemann is given as I of alpha, so f of t. We will extend this result as by putting alpha is equal to 2, as we put alpha is equal to 1 and get this result. Similarly, if we put alpha is equal to 2, and then the Riemann integral will be equal to alpha a raised to power 2, and which is summation I from 0 to n, and the gamma result will be as alpha is 2, so the gamma will be I plus 2 and I factorial to gamma of 2, f of t minus I of h. As we know the property about the gamma and the relationship between the factorial functions, so it's given as, so if we put I plus 2 gamma here, so the result will be I plus 1 factorial. If we open this factorial function, the I plus 1 into I of factorial. If we substitute this value of I plus 1 into I factorial into this, the I factorial and I factorial will be cancelled out and the value of I plus 1 will remains here. And if we take gamma of 2, there will be 1 factorial and the 1 factorial result will be equal to 1, so this value turns into 1. So the relation will be is like as, if we substitute I by I minus 1, so the result will be, the limit will be same, summation will be same, and the a square. As I replaced I plus I replaced by I minus 1, so the 1 plus I minus 1, so minus and plus 1 is cancelled out, so here's only the minus 1, and if you replace t minus I minus 1 into h, so the result will be t minus I into h, and minus minus plus 1 multiplied by h is plus h. Okay, here's h2, that will be divided into two values of h. One if we put with I, so I of h, and the second h is multiplied here. Okay, let me put t plus h is equal to y, which is a variable, as t plus h is the extension of the rectangles, so we can say it is any variable, that's name will be y. Okay, so if we take y is equal to minus I of h, then what will we do here? We will convert into the integral form, as I converted this form into the integral. So here's the form is also as t minus I of h. Here's I of h. I take this I of h as x. Okay. So here's also I of h is taken as x, and the y is transformed into another variable, which is so it converts into t, and this I of h is same as x. Okay. If we make same substitution of h here, t minus a into 0 over n, or t minus a minus 0 over n, so take h as same here, because the partition of each rectangle is same, so here's the partition of each rectangle will also same, so h will be same as it. And if we substitute again use t minus x, then the again by same substitutions, again same conversion of limits, as x goes to 0, u will be turned into t, and if x approaches to x minus a as mentioned there, the u will be turned into a. So our result, this integral will be turned into minus of t of a into t minus u into f of u into d of u. Okay. To remove this minus, we will switch these limits of the integral. So that will be upper limit will becomes lower limit, and lower limit becomes to upper limit, and t will sign will be vanished here. So t minus u f of u into d of u. Okay. If we extend this result to I3 by substitution again same values and taking the same procedures, the value will be 1 over 2 factorials will be here. Okay. So t minus u is 2 hairs and f of u and d of u. If we extend this result to the nth order of the integral, okay, remember this integral is a classical calculus integral, and the n is the positive integer. So by using these results, here the factorial is less than the order of the integral, so less than 1. So here's if the order of the integral is n, so the factorial will be n minus 1. And here's the power is also is less than 1 to the order of the integral, so here's the power will be n minus 1 f of u into d of u. As we are working about the fractional calculus, so we need to find the integral of the arbitrary order. So we replace n by alpha which is the ordinary number, which may be a real number, which may be a. So here's the formula of the Riemann Liouville Fractional Integral. So this formula may be helpful for us to find the integral of the sum function. In the next video we will see about the Riemann integral of different functions. So wait for the next video. Hope so you understand the concept of the Riemann Liouville integral. So we will meet in the next video. Allah Hafiz.